So I'd like to thank the organizers, Professor Adhikari and Professor Ramana, for inviting me. So I would be talking on discrepancy of generalized polynomial. So let me just write down that title. So discrepancy of generalized polynomials. So I would start with what is called a generalized polynomial. To define the generalized polynomial, I must fix that notation. So for a real x, so I would just write the floor function like this because I'm not going to use the ceiling. So this is the largest integer smaller than x, and the fractional part is x minus this is, so this is always going to be in 0, 1. So roughly speaking, a generalized polynomial, so a generalized polynomial is a polynomial which involves which is written with the operations bracketing, both these brackets, in addition to the plus and multiplication. So I would also formally define it. So a formal definition would be inductive. So I define this like this. So GP naught is simply all polynomials with real coefficients. So this is just the polynomial ring, and then GP, so I just define inductively, so GP of n is of course GP n minus 1, then union of all the sums of the elements here. So it is u plus v such that u and v is in GP n minus 1 union u v, the product u and v in GP n minus 1. So far it's just the polynomials. I haven't done anything new. So this is the part which is not done in usual polynomials. So that is the box of u with u in GP n minus 1. So that's an inductive definition. And so the examples. So examples are just can be generated like this, that if you just take a polynomial and put these brackets wherever you wish. So essentially that's a generalized polynomial. So if P1, P2, P3 are polynomials in Rx, then P1 box and P1 plus P2 box, or P1 plus P2, P3, and you can also nest these brackets. So these you can have nested bracketing. So all these are generalized polynomials. So I would also like to give some connections. So as to why we should study such things. Sorry? Yeah, so okay, so so we would be thinking of these polynomials as functions. So just think them as functions. So all polynomials are thought of as functions from R to R. R to R. So if so, a box of a polynomial is again a function from R to R. R2 in fact Z, so this is just going to take x to pi of x and then box. Yeah, so it's actually landing in Z. So polynomials are all thought of as functions. So before I go to discrepancy, I would be talking about uniform distribution. So the classical Wiles theorem in uniform distribution of polynomial values can be stated in terms of generalized polynomial. So let me just state that theorem. It's exactly the same theorem. So due to while. So let Pn be a polynomial. Or you can just, to start with, you can just write an x, the variable, xi 0 to n. So that's just an n degree polynomial in with real coefficients. And so if it has at least one irrational coefficient, if at least one of is irrational, then the generalized polynomial given by the curly bracket of Pn. So considering it as a sequence, so this is uniformly distributed. In 0, 1. So that's just the classical Wiles theorem just stated in this language. So let's see examples of generalized polynomials which are uniformly distributed. So before that, I would just want to recall what is uniform distribution. So let me just be quick on that. So if a sequence an in 0, 1 is uniformly distributed, if so what you are going to do is to count the number of n up to certain n. Okay, just let me write it down. So we are counting the number of elements of that sequence which lies between an alpha and beta. So alpha, beta are real numbers between 0 and 1. So between alpha and beta, and then divided by this capital N. And if this goes to beta minus alpha. So beta minus alpha is the Lebesgue measure of this interval which we are considering, and this should hold for every such interval. So for all such sub-intervals of 0 and 0, 1, so this is alpha less than beta less than 1. So if it holds for every such alpha and beta, and there were some equivalent conditions. So the first equivalent condition is the following: for all integrable functions, Riemann integrable functions, functions h on 0, 1, is some so h of an n less than equal to n, 1 over n. This so this mean converges to the integral. Converges to the integral, so that is equivalent to this. And another equivalence is the following, that you can simply consider the exponential sum. It can be written in terms of exponential sum. So this is summation E of k a n n less than equal to n, 1 over n. So this goes to 0 for all non-zero integer k. For all non-zero integer k, where this e of x is e to the 2 pi I of this. So this is e to the 2 pi I k a n. So if that goes to 0. So of course exponential is an integrable function and the integral is 0. So this immediately implies this, but it's actually equivalent. So these are the three equivalent criteria to see if a sequence is uniformly distributed. So there's a slightly general version of this. So this is what we are talking about with respect to Lebesgue measure. So some sequence can be uniformly distributed with respect to some other measure. So in that case, we change it a bit. So an is uniformly distributed with respect to a measure mu on this interval 0, 1 if just modifying this condition. So if this happens, that 1 over n summation h of an converges to the integral of h, but now not respect to Lebesgue integral, but the integral with respect to this measure d mu. And if this happens for all integrable functions, so all integrable functions with respect to mu. So we would see some examples where we would see that if we modify this measure a bit, then it's uniformly distributed, but it's not uniformly distributed with respect to Lebesgue measure. So let's just go to examples. Yeah, we would really don't need the formal definition, so I would just erase this. Yeah. If it is uniformly distributed, yeah, I think so. Yeah, I think so. Should be. Okay, so here is the first example. Yeah. Okay, so I should also mention that this theorem is actually known and in fact proved by Weil himself. So it is it's known for multidimensional cases. So what I just mean is this kind of thing is known, that if you look at a sequence, if you have a sequence of polynomials with all of them has irrational, at least one irrational coefficient. So so if you have the P1n, P2n, some pk of n, so all polynomials with irrational coefficients, so then this is uniformly distributed, so all this of course with the brackets, all with the brackets. So then it's going to be uniformly distributed, so UD, I just write UD in the k-dimensional box. So this is a multidimensional version is known. So we would need to use it actually. So to illustrate some examples. So let's start with an example. Yeah, of course I have taken easier examples. So some examples can be quite tricky. So these are can be easily handled. So an is square root of 2n. So it's not square root of 2n, it's square root of 2 is the coefficient n, and the bracket square, and then with a square root of 2. And we are considering it modulo 1, meaning the fractional part. So just saying it modulo 1 or saying that it's the fractional part is just same. So it's just a terminology. So this is the same. So we would try to prove that this is uniformly distributed. So uniformly distributed, so we are going to use one of these criteria. So we choose to use this criteria, so to make things more amenable. So we use this criteria. So let's start with that. So so before we start, we can write this in a better format. Square root of 2 is minus 2 square root of 2n square plus so square root of 2n and then a square. So these two are equal modulo 1. So I mean the fractional parts are equal. So by just saying modulo 1, I mean that the fractional part of the right hand side and left hand side are equal. So the exponential sum we need to consider is this. Yeah, sorry? No, it's not. This one? Yeah, it is minus, and that's the trick actually. So, yeah, I mean, just by opening the square, you won't get this. So it's a bit of a trick to get this. So this is yeah. So what we are looking at is this sum. Yeah, of course I have dropped some integer here. So because it's modulo 1, so I have dropped some integer. So of course, I mean, that's there. So yeah, so that will take care of the sign actually. So now, so what we need to consider is this exponential sum and show that it goes to 0 as n goes to infinity for every k. So let's write down let's write it down using this. So I have 1 over n exponential k minus 2 square root of 2 n square plus square root of 2, yeah, another bracket. Yes, I think I should erase this and yeah. So this, yeah. Now let's define a function. So let fxy is defined by exponential of k minus x plus, so the fractional part of y squared square root of 2. That's a function we define. So of course we intend to use it here. So this function is Riemann integrable. So f is Riemann integrable. It's a periodic function with period 1. So this is Riemann integrable in two variables. So on the box, two-dimensional box. So f is integrable on 0, 1 this box. And what we have here is, so this exponential sum is in terms of x, it is just f of 2 square root of 2 n square and square root of 2 n. That is how I have chosen the function. So it is just x is this, and the entire thing, and y is just this.
Curly bracket outside y.
Yeah. I don't. Yeah, I really don't need to put. No. Yeah, if I am choosing between 0 and 1, then I don't need. Yeah. No, but I would be putting square root of n. So I would need actually. I would need, because I would be putting square root of n, which is not in 0, 1. So I would actually need. Yeah, if I put something from 0, 1, then it's fine. But I would be putting square root of 2n. So in place of y. So I would require, yeah, I would need that. It's actually fine both ways. So you can define it as a function on all reals and then put a, maybe I'll just go with that. And just the domain is anything. So I can just put these values. Now, then it is integrable. No, it's a periodic function. So yeah, this is a periodic function of period 1. So I mean, this will take care that it's periodic of period 1. So yeah, so if I just do it like this, then it is so it just boils down to functions on 0, 1. So it's periodic. So it's periodic with period 1 in both variables. So it is. It's integrable. That would be easy to see, and the sum we are looking at is exactly this, n up to n. Now we invoke Wiles theorem in 2 dimensions. So these 2 sequences, they are polynomial sequences and they have irrational coefficients, so they are equidistributed. So that is equidistributed. So 2 square root of 2 n square and square root of 2n, this is equidistributed. So uniformly distributed. So this is UD in box. So that's, yeah, from Wiles theorem. From Wiles theorem in 2 dimensions. So it is equidistributed. It is uniformly distributed, and that is what we are going to use. So now we are going to use this criteria. So in 2 dimensions, so obviously that will have a 2-dimensional, I'm not writing down that criteria in 2 dimensions, but it's obvious to guess what it is. So that is going to give us that this sum, so since this is, so this is going to give that this is, this converges to fx y dx dy. And if you just calculate that, that's going to be 0 because the variables are going to separate out. Variables are going to separate out, then the x integral would be obviously 0. So this is 0. And that is exactly what we wanted to prove, that this is 0 for every k. K is just arbitrary. So this is 0 for every k. So this exponential sum converges to 0, and that shows that the sequence we started with is uniformly distributed in 0, 1. How much time I have? Half an hour. This is correct or that's correct? No, that is covered by something. Okay, that 26. Okay, I would still quickly want to show one more example. Second example. So that's this example. So that also comes from Wiles theorem. So so I consider the sequence alpha n. So alpha is irrational. Then this alpha n, the fractional parts, are uniformly distributed in 0, 1. Uniformly distributed in 0, 1, that directly follows from Wiles theorem. So if that is uniformly distributed, then the square is not. So if I take the square of this, then it is not uniformly distributed with respect to Lebesgue measure. But this is going to be uniformly distributed with respect to the measure given by dx to square root of x. So what I want to say is that by changing the measure, you can make it uniformly distributed. So there is a measure of uniform distribution. So and this can be done for any generalized polynomial. So that is a very deep theorem by Bargelson and Liebman, where they prove that the generalized polynomials have a measure of uniform distribution. Okay. Another example, I would just mention that, which is I don't think I have time to calculate. So I would just state another example. Yeah, this one is fairly easy to calculate again using these criteria. And so if alpha and beta are irrationals and un is this sequence that alpha n fractional part, beta n. So the multiplying the fractional parts of alpha n and beta n. So here also we can do the same trick actually. So very similar. So since so we use the fact that alpha n and beta n. So if you consider it in 2 dimensions, then it is uniformly distributed by this higher dimensional version of Weyls theorem. I have erased that. So higher dimensional version of Weyls theorem. So then you can show that this is un is ud on 0, 1 square with respect to measure given by minus log x dx. So the measure is given by minus log x dx. So that so with that measure it's uniformly. So that's the measure of uniform distribution. That's also easy to calculate. It's just the same calculation. So you just use the look at the exponential sum and then convert it into the 2-dimensional Weyls criteria, and then just using that you can calculate. Yeah, sorry. This is 0, 1. Yeah, of course. Okay. So I think in the remaining time I would just go to discrepancy. So what is a discrepancy? So in fact it's there. So we'll just write it. So discrepancy. So discrepancy is essentially the difference between these two. So this is supposed to converge to this, and so we just simply look at the difference and the supremum of it over all possible subintervals. So so I have a sequence an. Just let me write it. So it's a sequence an in 0, 1. Then we define discrepancy dn of this sequence an is, so this is just a sequence inside. So this discrepancy is defined by, so we, as I said, that we look at the difference of these two. So alpha between alpha and beta, and count it divided by n. So here we would stick to Lebesgue measure, just the length of the interval. And sup of, so the supremum over all such subintervals, so which is so supremum over alpha and beta in this range. So yeah, this can be 1 as well. Yeah, so this is actually can be. So that's discrepancy. So as we have seen in uniform, as we know in uniform distribution, it relates to an exponential sum. Discrepancy also relates to exponential sum. So via Edos-Turan inequality. So Edos-Turan inequality. So just write that down. So dn okay, let me just write that first and then we talk about the so it's a precise inequality, so I want to write it with all the correct coefficients. So this is so that's the inequality, and this holds for all h give more bigger than 1. So this is 6 over h plus 1, 4 over pi, and then you have 1 over h, and then so there is an exponential sum here. And what one looks for is quantitative estimates of this kind of this in terms of n. So to just mention a couple of results. Maybe I just go this way, just erase this. Okay, so before I mention quantitative result, I also would need some definition of irrationality measure. So a real number R gamma is said to have irrationality measure t plus 1, t is a positive real number. So t plus 1 if for any non-zero integer and any epsilon if for all, so if for all non-zero integer and all epsilon m to the t plus epsilon is bounded below by is bounded. So this is the distance from nearest integer. So it's either the fractional part or 1 minus fractional part. So this is the norm of the element in 0, 1. So it's just the distance from integers. So that's easy to understand. And then what I'm saying is that if I multiply this by, so it's essentially giving a lower bound for this in terms of m. So this says that this is going to be, so you are looking at a non-zero integer, so this is going to be bigger than m to the m to the minus t minus epsilon. So there is some constant involved, some positive constant which depends on epsilon and gamma. Yeah. Yeah, so it's not necessary in the definition. So yeah, so if so if t is an irrational measure, then anything bigger than t is also an irrational measure. Yeah, I'm not going to the smallest. Usually, it's not done. So so quantitative discrepancy estimates are known when we know this irrationality measure. So this is just quote a result by Kuiper and Netherreiter. So if gamma has irrationality measure measured t plus 1, then dn of n gamma, this sequence n gamma, the discrepancy of that sequence is bounded above by n to the minus 1 over t plus epsilon, and this depending on constant depends on epsilon, this is not t. Yeah. So gamma and epsilon, so it's n to the minus 1 over t. And there is a omega result known of equivalent strength, so it is an optimal result. So here the sequence we are considering is just n gamma. Now we come to the generalized polynomials for this. So let me just, maybe I just see this here. So this is a theorem by Hofer and Ramana, where they look at discrepancy. So I have to write a few things. So the discrepancy, so they look at the generalized polynomial which is given by n alpha and beta. So alpha, beta are irrationals. Irrationals, of course, satisfying some conditions. So they look at the discrepancy of this. So you have two irrationals. So we need a version of a two-dimensional version of the irrationality measure, and that is what is I should define here. So that's defined in this way. Very similar to that, maybe I just define next to this. So this is irrationality measure of a pair of reals. So a pair of reals is said to have finite type T So the language here is just finite type. So finite type T if for all epsilon there exists a constant, positive constant, maybe depending on epsilon, such that m alpha plus n beta, so m and n are integers, so this is greater than equal to C of epsilon. C might also depend on alpha and beta, so maximum, okay, let's just write like this. So m of t plus epsilon, n of t plus epsilon. So the very similar thing, so we are doing for a linear form involving alpha and beta. So this is for all mn, all non-zero integers, so z2 minus 0. So that's called finite type. Now they have conditions on that. So the idea would be to find out discrepancy estimates depending on this t. So whatever the irrationality, so it's an explicit quantitative estimate depending on that t. So here also the idea should be the same. So and looking at this n alpha beta, so the assumptions they have are the following. So alpha beta are irrationals, so such that, so they have two conditions, one alpha and so one alpha beta are linearly independent over, so this is linearly independent over Q, linearly independent over Q, and this finite type conditions for alpha beta, so that's a pair, alpha and alpha beta, and beta 1 over alpha. So both are of finite type T. Finite type T. Then they estimated this to be n to the minus 1 over 3t minus 2 plus epsilon. So that's an explicit estimate depending on this t. So just mention another result. So just mention it here. So this is a theorem coming out of a joint work with Ramana and Vishwanathan. So we look at a generalization of this generalized polynomial. So what we replace this n by a polynomial in n. So we have a polynomial in place of n of arbitrary degree. So, and our assumptions are also alpha, alpha, beta. So we have only one assumption. So it's a weaker result with only one assumption. This is of finite type. Finite type T. So discrepancy, okay, I probably should not have written it here, it's actually quite huge. Just write it here. Yeah, so I have a polynomial Pn. Pn is a harmonic polynomial with real coefficients of degree d. And then the discrepancy estimate is the following. So just replacing the n by a polynomial, any polynomial. So this is less. So I have to write a huge thing here. So this is 2 minus d plus 2 and 2 to the d minus 1 plus an epsilon, and this depends on epsilon. So d is the degree of the polynomial. So here, of course, it's degree 1 polynomial, and they have this 3t minus 2, and we have this. So this is so degree is in our case is always greater than equal to 2. So this doesn't follow from this. This is a generalization, but this is there. So for other polynomials, but this doesn't follow from this. So how much time I have? I think I'll just briefly talk about the method of this kind of estimates, very briefly. So the main tool to use is ADOS to run inequality, and so one ends up with an exponential sum. So if you are looking at this sequence, then the exponential sum you are going to end up is E of Pn alpha beta, and there is an h. And n is from 0 to n minus 1. So you can just open the bracket and write it as Pn of alpha minus Pn of alpha fractional part then you have this Pn alpha h beta, and so this is the fractional part that remains. So this is Pn alpha h beta, the minus sign, and we define a function f of tau x to be exponential So we define a function like this. So then the sequence, the exponential sum, not the sequence, the exponential sum reduces to and then you have f of minus h beta Pn alpha. So just using this notation. So then we approximate, so that's the problematic part. This is the traditional thing. So that's a bit of a, that's the main part which we need to handle. So then this thing is approximated by a slightly smoother function. So what we do, we take a delta and then look at this function. So g of, so maybe just write with this general notation, not to make so much of notation. So this is a function g tau of x, which is defined in this way. So I take the indicator function of the interval minus delta to delta and convolve with itself r times. So that's r times, and then convolve with f tau of x. Yeah. So then convolve with f tau, and then just normalize with respect to the measure of this box. So that is minus delta. So that is 2 delta power r. So just this convolution with the indicator functions and r times, and then just normalize with respect to that box. So the advantage being that when we consider the Fourier transform, then we would get a good saving from here. So what we do, we replace this by the approximation, so that then we are in this situation. So I have g minus h beta Pn alpha, and then obviously we have done this to write down the Fourier series, so we would write that. So I have this n sum, and this is now expanded into the Fourier series. So the Fourier coefficients will have good decay in terms of k. So so this is going to have a very rapidly converging tail because of this. All these convolutions will give a lot of saving in terms of k. So it will be rapidly decaying. So then you have E of minus k Pn of alpha. So by interchanging summation, so since this has very good decay because of this smoothing, so this is going to have very good decay in terms of k. So it will be decaying like 1 over k to the r. So because of that fast decay, the tail would rapidly converge. So that will so it will essentially boil down to a finite sum, and this is a more traditional exponential sum. There is no bracket involved in that. But of course, the issue here is to estimate this sum, keeping this part intact, because you are going to sum over k and then you are going to sum over h. So you need explicit dependence on h and k. So, okay, I think with that I'll stop. I'm over time.